Hi, everyone. Please welcome Ariel Gabizon from Aztec, one of our lead sponsors. Ariel is the chief scientist at Aztec, and he'll be delivering a talk on FFTs on the projective line. Please give him a big round of applause.
Okay, thanks. So as a disclaimer, I sort of realized this last week, this is not a good topic to give a 30-minute talk on. The reason I thought it would be is I gave a 20-minute talk on this a few months ago, and I thought it went well. But after watching that talk 20 times to increase the number of views, I realized actually that it wasn't a good talk. It didn't really explain the the subject. So with that disclaimer, let's start. I hope you'll find something interesting here. So let's start with a reminder of the classical FFT. We have some subgroup in our field of size that is a power of 2. And we want to evaluate some polynomial of degree smaller than n on this set. So we use the following recursive formula that I'm guessing most of you have seen in your life. We write f as we decompose it to the even and odd coefficients. We can write f as f even of x squared plus x times f odd of x squared. And because the mapping going from x to x squared is a 2-to-1 mapping on S, right? Because if we look at all the squares in the set S, we'll get a set of half the size. Then this formula reduces these n evaluations of f to n over 2 evaluations of these two polynomials of degree n over 2. And we can continue like this because the set is of size of power of 2, and this gives us the classical FFT. But this requires n to be to divide p minus 1, where p is the field size, because otherwise we won't have such a subgroup S. So a question that people recently in Snark world, Snark land, have been very interested in is, can we work with n when n divides p plus 1 instead of p minus 1? Can we have a fast FFT? Why are people interested in this? Because they want to work with the simplest field possible in terms of its representation in binary form. And that's what's called a Mersenne prime, where the p is 2 to the k minus 1. So, for example, everybody's working now with 2 to the 31 minus 1. And then, obviously, in the case of a Mersenne prime, p plus 1 will have a large power of 2 inside of it. So that's the question the talk focuses on. Can you get a fast FFT when n divides p plus 1? And the central idea, one of them, is that really the main thing you need is a set with a cyclic operation on it. So again, looking at the classical FFT from that viewpoint, we have the map x goes to g times x. And this map sigma, x goes to g times x, it goes over S in a cycle, right? You start from any point in S, you apply sigma repeatedly, then you will go over all of S. And let's see how all the FFT can be sort of derived from sigma. So we can define tau to be sigma to the n over 2. So sigma applied n over 2 times. And you can check that in this case, tau will just be the mapping x goes to minus x. And just from the fact that sigma is a cycle, we get two things. So we get, first of all, that tau has order 2. Tau squared is like sigma to the n, so it's just the identity operation. And because of that, S will split into disjoint pairs, A tau of A. And now, right, a main component in these FFT algorithms is a 2-to-1 map. So we can define the mapping n of x to be x times tau of x. I call it n because it corresponds to the norm of a certain field extension, but that's not important to know. And now I claim that this n will always be a 2-to-1 map on S. Why? Because, right, if you do n of A, that's A times tau of A. And if you do, because it's of order 2, then if you do n of tau of A, you'll get the same thing. So n gives us this 2-to-1 map. Right, so we got all of this just starting from some cyclic operation on the set S. So can we find, since we want to work with p plus 1, can we find a set of size p plus 1 with some cyclic operation sigma on it? And this naturally brings up what people call the projective line. So what's that? That's where we take our field f, think of it as points on a line, and add the point at infinity. So of course, this is a set of size p plus 1. And how are we going to operate on this set? We're going to look at fractional maps. We're going to look at the map going from x to 1 over ax plus b for some fixed a and b. And we want to think of this as an operation on p. So there's 2 points where you're a little unsure what to define. So for example, the point minus b over a, it's going to make the denominator 0, so 1 over 0. So let's say that sigma maps minus b over a to infinity. And we need to say what sigma of infinity is. Well, that's kind of like 1 over infinity. So we'll say that sigma of infinity is 0. Okay, so we defined the map sigma, and indeed in the you can look in the paper of Li and Xing and see that really there is some choice of A and B such that sigma will be a cycle over all of the projective line. So you might have been hearing the term circle Stark lately a lot. So a lot of times people look at the projective line as a circle in the plane. The way you do this is you draw a circle above the x-axis, And then to map the circle to the exit to the line, you to see where a point maps to, you draw a line between the north point of the circle to the point you want to map, see where it meets the x-axis, and that's the point that in the line that the point in the circle maps to. And then you ask, well, the point on the north, where does it map to on the line? It'll, right, because it'll just be like drawing a tangent line to the circle that won't meet the line. So we say, well, that north point maps to infinity. Or you can alternatively just think of taking the x-axis and kind of bending it, and then sort of the point at infinity will map to the north point of the circle. Okay, but back to, so now we have, right, so we said all we need is a kind of a cyclic operation to get an FFT, so it's not going to totally work out, so let's see what happens. So let's try to proceed as before. So now instead of the mapping sigma x goes to g times x, we look at this fractional mapping. We know it goes over all the projective line as a cycle. And again, we can define tau just to be the map sigma to the n over 2. Apply sigma n over 2 times. And we know just from the fact that sigma is a cycle that whatever mapping this tau is, it will also divide p into disjoint pairs. Okay, now let's try to get the 2-to-1 map. So again, we can try to define n of x as x times tau of x, and try to say that it's 2-to-1 on p. But now we get into a problem because p is not a group, so a times tau of a is not defined. So here we kind of get stuck, and we need to go a little into algebraic geometry or algebraic function field theory, and go to a sort of different view of the point A. So this is where it gets a little more abstract or algebraic. So let's call K the field of rational functions over F. And now, given some point A in the field, let's match it with this set PA. So PA is all functions, rational functions that are 0 on A. So P of A is called in algebraic geometry or the theory of algebraic function fields, it's called a place of K. And for those familiar with the term, so P of A it turns out to be the unique maximal ideal of the subring of elements that don't have a pole at A. So the reason we can think of P of A as like an algebraic representation of A is that, like, what can we do with A? We can evaluate functions at A. So this evaluation, you can do it in a more abstract way using PA. So let's see an example of that. So fix a polynomial f. We have to work with rational functions, but for simplicity, let's talk about a polynomial. Say we want to evaluate f at a. So we can write f, instead of in the regular monomial basis, in this basis of monomials of the form x minus a to the I instead of x to the I. And let's call this part, the non-constant part, let's call it g. So substituting a inside these equations, we can see that, well, g is going to be 0 on a, right? Because all these monomials, x minus a to the I, they're going to be 0 at a. So g is going to be 0 at a, which means it belongs, by definition, to this PA. And this constant c, right, if it's going to be equal to f of a, right? Because on the left-hand side, you have f of a. On the right-hand side, the only thing that is not zeroed out is this c. So in other words, we can evaluate f at a by taking f mod PA, by like writing f as some constant plus some element of PA. So that's why you can think of PA as like an algebraic representation of A. The nice thing about these places is that we also have a representation for the point at infinity. This is going to be the place P infinity, which is going to be all the functions f over g, where the degree of g is larger than the degree of f. And right, it makes sense that this is sort of the functions that are 0 at infinity. Since the denominator has larger degree, it's intuitively the functions that are 0 at infinity. Okay, so now we want to use this framework of places to sort of get this FFT to work with this fractional map and not get stuck, to get somehow this 2-to-1 map we need. But to exemplify the ideas more easily, I'm gonna work with a tau from the regular FFT. Let's just think of tau of x is minus x. So the first thing we need to think about is, right, this tau was a mapping from the field to the field, or say from the projective line to the projective line. We need to define it on these places. So how do we do that? Well, first, we can define tau as an operation on the field of rational functions. How? Just by sort of substitution. We have some rational function r of x. We're going to change the inner x to minus x, and that's it. So tau of r of x is r of minus x. And now we need to say how to apply tau on a place. So, right, a place is just this set of functions that is 0 on A. So we're just going to apply it element-wise. We're going to define tau on P of A as just the set of functions tau of R over all of R in PA. And the cool thing is that this acts like just the natural map x goes to minus x, right? Because this gives us all the functions r of minus x, where r of a is 0, because we're in PA. So those are exactly the functions that are 0 on minus a, so which is p minus a. Okay, so now we need to do two more steps to get our 2-to-1 map. The first thing, we're going to look a lot at subfields, at what's called Galois subfields. Specifically, we're going to look at the subfield of K that is fixed by tau. So all the elements are such that tau of R is simply R. And you can check that this is f of x squared, so all rational functions in x squared. For example, if we apply tau just on the function x squared, so what does this look like? It's changing the x to minus x, and then doing the squaring, so we get back to x squared. A lot of the theory of algebraic function fields is about how places, quote unquote, split in extensions. And we're going to see an example of that right now. So again, look at some A in the field and let B be A squared in the field, like the base field. And let's look at the place P prime B in this subfield x squared. What does it look like? So by definition, it's all rational functions R in x squared such that R of B is equal to 0. So for example, let's forget rational functions. What does a polynomial in P prime B look like? It's going to look, we can write it like this, like similar to before, as a combination of these x squared minus b to the I. And since R of B is 0, f of B is 0, there's no constant term. Okay, but now we can apply the well-known algebra equality. This is some combination of x plus a to the I times x minus a to the I. So definitely it's going to be 0 both on a and minus a. So in our terminology that we defined, it means that everything that is in P prime B is going to be also in PA, but also in P minus A. So we had this place of the subfield f of x squared, and when you go up to the field K, f of x, it's going to be contained in two separate places. So we say that the place splits into two places. By the way, and I think this is a good time for, can I ask for questions? Yeah, this might be a good time for questions. We're pretty close to the end, but yeah, I think it might be a good point if there are any questions. I think you got one over there.
Why do both terms x plus a and x minus a have to be 0 and not only one of them?
Well, if you have something that is a combination of x squared minus b, so it's going to be, right, a combination of x plus a times x minus a. So that implies that it's 0 both on a and minus, because it's a combination of those. It's going to be 0 both on a and minus a. If you're a combination of things that look like x plus a times x minus a, then I think you have to be 0 both on a and minus a.
Thank you.
Okay, let's continue. We're pretty close to the end. We can. Okay, so now let's try to tie it together. So right, so our goal was to define this 2-to-1 map N. So now a slight sort of formal change. If before we were talking about the projective line, we're going to think of P as all the places corresponding to the projective line. And as before, we know that sigma goes over P as a cycle. We can define tau to be sigma to the n over 2. And we know that P will split into disjoint pairs, P tau of P. And now we come to the sort of the punchline. So how do we define a 2-to-1 map? So let K prime be the subfield of K of elements fixed by tau. So it won't be this, for whatever tau we're going to get here, it's not going to be this field f of x squared. It's going to be some maybe other slightly more complicated field. And now define n of p. So we're going to know, I mean, I haven't gotten into this, that every place of K prime is going to split into exactly 2 places of K. So we're just going to define n of P to be the place of K prime that splits into P and tau of P in K. And okay, so that's a basic idea. For more details, I recommend the paper. And for a more elementary approach that ends up actually having better final FFT constants, I recommend looking at the Circle-Stark paper. Yeah, so thank you.
Thank you, Ariel. And any final questions from the audience? Okay, thank you so much, Ariel. And once again, a big thank you to our sponsors, Aztec,